Hello and welcome to Physics Frontiers, episode number 64, Whence Born's Rule. Show notes for this episode can be found at frontiers.physicsfm.com/64. Show notes include the papers we read for this podcast, books we may have mentioned in this podcast, including A First Course in the Sporadic Seeks by Blake Stacey, and previous episodes of Physics Frontiers, including the previous episode of which this is a continuation. When I talked with Blake Stacey of the Quantum Information Group at UMass Boston, we had a long discussion about three things: Gleason's theorem, the Born rule, and SEEKs, symmetric informationally complete positive operator valued measures. All of these are in a similar place in quantum foundations. We were discussing Gleason's theorem in part because the commentary I found of Blake's on the archive about the Born rule and recent attempts to replace it, which is what this episode is about, heavily relied on Gleason's theorem. And so those are these two episodes. We talked about the SEEKs because Blake and other people are trying to do similar things with the SEEKs in quantum foundations. And so today what we want to talk about is the Born rule. In fact, what we're looking at specifically is whether or not it's possible to replace the Born rule with something simpler or something more obvious. And now, Blake Stacey.
Yeah, and I think this is where I wanted to get to, right? Which is, why do so many people want to take the Born rule and turn it into a consequence of either those other axioms, whatever they want to call those axioms, or those other axioms plus some new things that they might find a little more natural than the Born rule, I guess. Because, I mean, it sounds a little bit like Euclid's fifth to me.
That's an analogy I was thinking of bringing in myself, that where you're kind of in that Euclid's fifth postulate situation, where you have four axioms that you're like, oh yeah, of course, and then one which is a paragraph longer than all the others, and it's like Euclid's original statement is just, these are, you've got lines and a line intersecting them, and if these angles aren't right angles, you're just going, okay, where did that come from? And then people, in trying to prove it from the other axioms, they successfully found ways of restating it, or things it could be replaced with. Playfair's version was, given any line and a point not on that line, there is exactly one line through that point parallel to the given line. Simpler than Euclid's version. And so, progress was made in improving on Euclid's presentation, but it was eventually found that no, you can't just deduce that from the other rules. In fact, you can replace it with something else and obtain another consistent geometry. And the question is, are there things like that in the mathematical structure of quantum theory, where maybe we can pull this rule out and either deduce it from what's left, or maybe there's something else that can be put in that spot and give another consistent structure. There was recently some interest stirred up in, why does quantum mechanics use complex numbers? There are different ways one can get at that question, but if one of the first things you bump into when studying the subject as your first, second year of college, and suddenly you're dealing with square roots of negative numbers, and it seems like they're not just an artifice for convenience like they are if you're talking about electrical engineering or oscillations of waterways, this really unavoidable feature of the math that you can't get away from, that the thing which you're calculating with always involves this larger number system than just a one-dimensional number line. But you don't go further than that. You don't use quaternions or octonians. You don't use p-adic numbers. You use this particular number field. And are we just obliged to take that as a given? Well, you can, and as an undergraduate, in order to solve the homework problems, you accept these rules, and they work out in practice. But is that the only mathematically necessary option? No. You can, in fact, formulate what you might call a character foil theory to quantum mechanics, where there are no complex numbers. instead of Hermitian matrices, just have symmetric matrices. Or you could go even further. You can formulate a character foil to quantum mechanics which uses matrices of quaternions instead of complex numbers. Things work somewhat differently. That gives you a way to get your hooks in and say, okay, this theory works differently. What's preferable about the complex options? That's the one we want to select. So you can look at the ways in which the real vector space and the complex vector space and the quaternionic module theories work differently and say, aha, it's the complex vector space theory that has this desirable property. I will then take that desirable property as a basic rule. And then if I'm ever challenged, why use complex numbers? Well, it's to have this desirable property. There are different candidates for that desirable property, though, depending on what you like the most, what you really want to pick out as a significant feature, and what you're taking the other givens to be. So when you're playing around with this, quantum theory, it's like a gemstone. It's like you have this precious jewel. And when you first meet it as a student, it's kind of, maybe it's set in an ugly band, but you become more familiar with it and you detach it from the ugly setting and then you hold it up to the light. Then you find that you can rotate it and catch the light at different angles and bring out different features of this very intricately carved jewel. You can bring out one facet or another, maybe one facet or another to look more important to the overall structure, but it's not yet clear, how did that crystal grow? Did that crystal grow from a single seed? What's the reason for the structure? We learn more and more about the different ways of appreciating it, but we're still missing that key insight. It says, this is what's really strange and weird and interesting about the theory. And all these other things are deducible consequences. Maybe some of those deducible consequences depend upon our conventions for how we find some things convenient. We're still at the stage where, all right, we can rotate the jewel this way, rotate it that way, and then see, okay, see this facet or this other facet. We're still trying to go from that stage of understanding to this is where the jewel that is quantum theory came from. And Gleason's theorem and these other things that I was kind of discussing in that context is part of that history of learning different approaches to quantum theory from which one can appreciate it and understanding the different ways one can take out a piece and see if that piece can be reconstructed from what's left over.
I guess that got us all the way from one question to the next, right? To summarize what I think I heard you say is part of the reason why people are playing around with the Born rule is for the same reason as you were looking at why the complex numbers, which is trying to look at the structure of quantum mechanics and find out what the principles are, the way you'd have the equivalence principle in relativity, where you have something that sounds a little bit more like a logical principle rather than a bunch of rules that you have to follow. Otherwise, you get the answer wrong. But what I'm trying to get at is when we move on to look at your paper and how these other two papers more or less do the same thing as Gleason's theorem, what is the kernel that we want to look at from that discussion?
A couple other papers from the past couple years are taking different perspectives on the jewel that is quantum theory, looking from different angles, and also asking, can we take some pieces out and regenerate them from the axioms left behind? So Gleason took out the specification of the state space and the rule for calculating probabilities given an element of state space and a representation of a measurement, and showed that you could derive those from a context independence assumption and your other axioms. Then there are other pieces that you consider taking away, and there are other ways you could think about imposing conditions on what measurements should satisfy. So the first of the two papers I was talking about, Massanes et al., was eventually published in Nature Communications.
I don't recall.
I saw it in the archive, and the nice thing about the archive is it's there to be read, and usually when a multi-author paper gets as far as the archive, the math in it is probably right or close to right. And then the question becomes, are the assumptions reasonable and are the conclusions drawn from the math reasonable? Because usually when people who have a record of publishing things get so far as putting a new thing on the archive, they've checked enough that mistakes won't be in obvious places. What they do in this paper is they take a list of...
I think it's 5 postulates is what they have.
Yeah, so more or less what Mackey did, they find, all right, this is what we mean by quantum theory. And they say, okay, we're going to pull out, we're going to remove from that structure a couple of the statements, and we're going to derive them back again from what we have left over and some more conceptual, you might say qualitative inputs. Then they do the calculations and they get the result that, yes, we come back to the starting point. We've reassembled the structure of these 5 defining postulates for what we mean when we say quantum theory. And they don't take away the same pieces that Gleason did. Their starting point is probably what is more instinctively acceptable to physicists who have the intuition that the state vector is the thing that is physically there. And it's like what I first thought the electromagnetic field would be when I first learned electromagnetism, and I thought that was a fundamental theory. They want that to be the rock on which the theory is built. And so they're in that column of Cabello's map of madness. Mathematically, they start with a specification of the state space, and they want their underlying state space structure to be basically a d-dimensional complex vector space with a phase degree of freedom thrown out. So projective complex space. And then they want to assign probabilities to measurements given that a state is an element of this state space that they have defined. So then they put in some conditions on what measurements should be like. And to me, it's kind of an interesting mix and match of concepts because, okay, we start by assuming a state space, which is not what Gleason did. And then we make some assumptions about measurements. On the one hand, you're assuming a state space. But on the other, you're making this move that's coming almost from a different tradition. We're saying, okay, I will take measurement as a primitive notion and just specify mathematically what I mean by that. And then I will make deductions. One philosophy would be, as long as you're clear about what you make your fundamental assumptions to be, then you're good.
Yeah, I mean, mathematically, if you remove 2 assumptions, if you remove 2 postulates, and you add 2 other postulates, and you end up with the same thing, at least mathematically, that just means you've done nothing, basically. The question is which, I guess a question to a physicist might be, which is more natural? But I'm not completely sure that one is more natural than the others. I mean, the star function seems just to be a combination operation of some kind to me. I'm not really sure how natural that feels. It still feels mathy, I'll put it that way, but not really more like a computational mathematics instead of postulate mathematics. Does that make sense?
Yeah, and what I said in my little note about this was that instead of doing that mix and match, you could use their same methods of proof and do something more like what Gleason did. Say, okay, the underlying language we're working with is the language of Hilbert spaces, complex vector spaces. But we're only specifying a notion of measurement. As I recall, Gleason's assumption was that a measurement is an orthonormal basis. Well, you could use the theorem proving from this paper and say, instead of specifying a state space, that the state space is this set of complex vectors, mod phases, you could say among the possible measurement outcomes, the sharp measurement outcomes are the d-dimensional complex vectors mod phases, and then prove the same theorems, just swapping out what some of their acronyms mean and making them assumptions that are all about measurements rather than this mix and match approach. In which case, you'd end up with something that's more akin to Gleason's theorem, which starts with Hilbert spaces and then defines the notion of measurement and then deduces from there. You could do something more like that with their style of theorem proving rather than this, all right, we assume the state spaces and then we try to derive measurements given some properties of what measurements ought to be. You could just say, okay, let's talk about what measurements ought to be. So that this is carving up the theory in different ways or looking at the theory from different perspectives.
Basically, you're saying that you think that they could do more interesting things with this.
Yeah, I think that mix and match approach it kind of muddies the waters a bit. When you bring in a concept from over here and a concept from over there, and then, as written, as published, it's a bit hard to see where to go with these ideas. So might help to, okay, can we do the same style of theorem proving, but with assumptions that are all of this kind rather than some of this kind and some of that kind? Just give a better appreciation of how it's all fitting together.
I mean, at the beginning of this paper, they talk about all the different ways people are doing almost the same thing. And they're doing the same thing. They're mixing and matching. They're saying, okay, well, if we can take, I'll read them from here. You can use quantum logic. People do it with the many worlds interpretation, apparently. And they try to get the Born rule out of that. And the entanglement assisted invariance, which I'm not sure what that is, and so forth. So they have like 22 papers here at the beginning that are all doing something similar, but they feel their particular postulates are more natural, I guess, than these other 22 papers. But it's still the same sort of approach, it seems to me, just choosing a different set. I guess that's good. I mean, it's good in a way. It's a way to sit around and argue for another 10 years over which postulates you should take out and which ones you should put back in. But I'm not sure to what level it necessarily helps. If what the big thing is you want to get rid of Born's rule, I really don't see where we're getting anything new out of this. And now the Hassenfelder paper, at least the claim there is that there's the only one. Born's rule is the only rule, and it comes from these other things without a lot of extra ontological baggage, I guess, or extra philosophical baggage. I think that's what her claim is.
Yeah, the original title of that paper was Born's Rule from Almost Nothing. It was published as something else. And very interesting to see how papers evolve from the archive to journals. So it's very much an attempt to eliminate baggage, kind of derivation. And whenever you say you're getting something from almost nothing, the question then becomes, how much work is that word almost doing? And the reaction I had was a very interesting approach, different from how people had gone about doing things in a similar spirit. But again, making assumptions both about states or the possible ways a system can be prepared and about how to represent a measurement effectively. Because in this paper, both of those sets are specified. You have the set of states as this set of vectors, and the set of possible measurement outcomes is the same set of vectors. And you're trying to make a rule for calculating a probability given a vector here and a vector there. And it is phrased in terms of transition probabilities. But basically, if Gleason's theorem said as little as possible about states, nothing directly about states, and assumed a notions of measurement, and the first paper we talked about assumed a notion of states and said some things about measurements. This paper says some things about both, and gives a quantitative, not qualitative or conceptual description of both. It says this is the set you're dealing with in both cases, and we want to rule, we want to function from pairs of vectors to probabilities, which is a fine thing to ask for if that's the assumptions you're willing to start with. And the conceptually interesting thing that came up, and we were discussing this briefly on, there's a platform called Scirate that looks at the archive and reads the titles and abstracts and authors from the archive and then gives a place to discuss and you can click to upvote, or
Okay,
click
yeah.
to give a this looks interesting kind of tally mark archive preprints, and used a fair bit by people in the quantum information community where it came from and who it's been adopted by. So there's a little discussion on that forum about this paper, and a very dramatic title, of course, and then zeroed in on this question of what's the almost and the almost nothing. And one of the points that came up was the question in that paper is to derive a function which assigns probabilities to pairs of vectors, initial vector, final vector, or a preparation vector and a measurement outcome vector. The rule is the probability is assumed to be independent of whatever basis that final vector might be living in. In Gleason's theorem, Gleason assumed that probabilities are non-contextual, context-independent. The probability I assign to the z hat unit vector is independent of whether I take that as part of x hat, y hat, z hat, or any rotation thereof that leaves z hat in place. And while you can always make that mathematical assumption, whether or not it's physically motivated is a different question. And this kind of this short little paper, it's nice when things are of a readable length, not 17 pages of double column, small print, supplemental information. The theorem proved in this paper neglected any possibility of that kind of context dependence. Now, if you're coming from the Dirac, von Neumann tradition of taking classical physics, taking the variables from classical physics and promoting them to Hermitian operators on a Hilbert space, and that satisfy turning Poisson brackets into commutators. If you come from that tradition of how to write quantum theories, then it's conceptually hard to see where that context independence assumption might come from, because the quantities of interest are the whole context. They're it's the whole Hermitian operator, because you've written the Hermitian operators by promoting classical variables and imposing canonical commutators. Well, then why should you care about individual eigenvectors of a Hermitian observable if the whole physical thing of interest was the Hermitian observable rather than the individual vectors that happen to be its eigenvectors? So if you're coming from that direction, where's the non-contextuality assumption coming from? You can always impose it, but where's it coming from? If you come from the quantum information direction, say, okay, my notion of measurement is a POVM. It's not the old von Neumann orthonormal basis Hermitian operator definition. And I'm taking this more modern approach to defining what I mean mathematically, then my notion of a measurement outcome or of a state preparation is something broader than just these vectors. My notion of a state preparation is a density matrix, and the set of pure states, the set of wave functions or state vectors in the old sense, those are just what lives on the outer surface of this convex body that is the set of possible density matrices. And specification of an individual measurement outcome is something more general than just a vector. It's a whole matrix, it's a whole operator. So coming from either of these directions, this theorem, well, nice and succinct, is just the question of the missing motivation, to put it in Sherlock Holmesian of terms.
Yeah.
So again, you're able to prove a theorem that shows you can look at the theory from a different direction, but why are you picking that direction? And what does that tell you about where to go next? And what the really mysterious aspect of the theory is? Something I find remarkable, which is only intermittently addressed in this whole body of literature on reconstructing quantum theory, which people have really worked a lot at since the turn of the 20th to 21st centuries. A lot of different papers doing a lot of different approaches to this. But their sets of axioms are almost always what David Mermin called benignly humdrum. Okay. They want to take a list of axioms that are as pedestrian sounding as possible, and then from them, by theorem proving, they get back to quantum theory or something very close to quantum theory. Then having rederived quantum theory, you can then go on to prove that it violates Bell inequalities and that it holds out this hope of quantum computational speed up. All these things having to do with resisting a description in terms of intrinsic hidden variables, gears inside the electron. Now, you might fairly ask, did that not just make everything harder? Instead of getting closer to this enigma of uncertainty that's very hard to wrap our minds around conceptually, have we not just distanced ourselves further from it by putting ourselves in a place where now we have to rederive the theory that we started the book with, and then chapter 7 in the book, we finally get around to Bell's inequality again. What I hold out hope for is a way of reconstructing quantum theory where you start with the dramatic and enigmatic aspect. You find some way of formulating a violation of a Bell inequality. You find some way of formulating the way in which quantum theory resists hidden variables, resists that mundane kind of source of uncertainty, and then take that as a fundamental axiom, as a physical postulate, maybe in conjunction with some other physical postulates, derive the theory. So you bring to the forefront, instead of pushing to the background, the quantum mysteries. It does seem to be possible. One of the things I've been taking stabs at over the past few years with some colleagues, and taking inspiration from all these other papers that have done various quantum reconstruction jobs, take bits of the math and say, ooh, okay, let's play that argument backwards. And you can find new representations of quantum theory, which are just in terms of probabilities, which is a weird and remarkable thing. Translate quantum theory into consistency conditions on probabilities between different conceivable experiments, and then find in those consistency conditions a candidate for a premise for a new postulate, and then derive quantum theory back out of that by saying, okay, this expression of consistency conditions between probabilities expresses a rejection of hidden variables. And we're putting that front and center. We're saying that's rule number one. And then by adding minimal assumptions to that, we can get back to quantum theory. Because again, to be honest, I have to say, what do I mean? How much work is that minimal doing? That's one of the currently unsatisfying things, is having to make assumptions that are more specific than we'd like. We don't want it to look like we just look in the back of the book and get the answers. You really want something that's not assuming a particular symmetry group. That's just a very mathy and unsatisfying kind of assumption.
Okay, well, I think that's excellent. I think it was a very good 2 episodes. And I think people will be very interested to hear about Gleason's theorem, and also for these Bargman invariants and the Seeks, because we haven't talked about them at all. Didn't know they existed until I saw them on the cover of your book. Right? So I didn't know about your book until after I invited you on here. Then I saw it here and I said, I wonder what those Seeks are. Yeah, so very nice. So we got that in as well. I'm very glad we had this conversation, and thank you very much for coming on the program. I think it's been very useful. I think people will really like it.
Well, I hope so. Thank you very much for reaching out.
You have just listened to Physics Frontiers episode number 64, Bourne's Rule. Show notes for this episode can be found at frontiers.physicsfm.com/64. Show notes include the papers we read for this podcast, any books we may have mentioned, including a first course in the sporadic Seeks by Blake Stacey, and links to related episodes of Physics Frontiers. These include episode number 63, as well as a Patreon link to the last half hour of this discussion, which deals with the Seeks symmetric informationally complete positive operator valued measures. I'll probably leave that for patrons only for a month or two until I remember to take it off, at which point I'll just let everybody be able to listen to it. So thank you very much for listening. I hope you do like the new format. I'll have another really great one next time. Bye now.